When reflecting on our exploration of Saturn, it is difficult to overstate the good fortune of having the Cassini-Huygens mission. Of the 4 robotic probes to have visited the ringed world, Cassini-Huygens was unquestionably the most consequential, both in the scientific sense and in the literal conclusion to its journey. The wealth of data it gathered has served as the bedrock for over 4,000 research papers, a legacy of immense discovery. During its tenure, it identified 6 previously unknown moons and deepened our knowledge of their composition. The spacecraft survived a 20-year voyage that spanned 7 billion kilometers, with 13 of those years spent in orbit around Saturn. In that time, it meticulously gathered information on the planet's gravity, its powerful magnetosphere, its iconic rings, and its internal structure. Cassini remained a diligent observer until its final moments, transmitting data as it plunged into the mustard-hued clouds of Saturn's atmosphere, where it ultimately broke apart into thousands of pieces. This incredible scientific return, combined with some of the most awe-inspiring images of Saturn and our solar system ever captured, defines a mission of historic significance. The genesis of this ambitious undertaking can be traced back to the Pioneer 11 probe, which first reached Saturn in 1979. It was during this flyby that scientists received confirmation that Saturn's largest moon, Titan, possessed a substantial atmosphere. This discovery created an imperative to return, but the next visit would need to include a lander. At that point, the Voyager 1 and 2 spacecraft were already well on their way to Saturn, making it impossible to add a landing craft to their missions. From this scientific need, the concept for Cassini-Huygens was developed, and the spacecraft was ultimately launched in October 1997. Propelling a probe to Saturn is a formidable challenge, as the entire journey is a constant struggle against the Sun's immense gravity, which perpetually tries to pull the craft back toward the inner solar system. To build the necessary velocity to reach its distant target, Cassini employed a series of gravitational assists, using planets as cosmic slingshots. It performed 2 flybys of Venus before swinging back past our own planet. Earth's gravity then propelled it toward Jupiter, which provided the final powerful push it needed to coast the rest of the way to Saturn. The specific alignment of planets that made these maneuvers possible is exceedingly rare, occurring only once every 600 years, making the timing of the mission absolutely critical. The precision required was remarkable. During its second pass by Earth, Cassini flew just 1,100 kilometers above the surface. This close approach to our homeworld is made all the more intriguing when considering what powered the spacecraft. Cassini drew its energy from 3 radioisotope thermoelectric generators, or RTGs. At the heart of this power system was approximately 33 kilograms of radioactive plutonium. The steady heat produced by the material's natural radioactive decay is what gave Cassini its electrical power, and even at the very end of its operational life, the system was still generating around 700 watts. The reason for using RTGs was a practical one. At the time, solar panel technology was not advanced enough to power a complex spacecraft so far from the Sun. However, carrying this radioactive material presented a notable risk. If the mission's engineers had miscalculated the Earth flyby and the probe had accidentally crashed, radioactive particles would have been dispersed across the planet. While 33 kilograms is a very small amount when spread over the entire globe, NASA estimated that in a worst-case scenario, the incident could have led to about 5,000 cancer-related deaths. The agency deemed this an acceptable risk, as the mathematical probability of such an event was calculated to be only 1 in a million. Thanks to the RTGs, Cassini was afforded a very long operational lifespan, and it might have continued its work even today were it not for the eventual depletion of its propellant fuel. The mission had a broad set of objectives, including the study of the structure and dynamic behavior of Saturn's rings and a more thorough exploration of its many moons. Scientists also aimed to measure the planet's magnetosphere, analyze its atmosphere, and, crucially, investigate Titan, in greater detail. This final goal is where the Huygens portion of the mission's name becomes significant. Huygens was a dedicated lander, designed and operated by ESA, the European Space Agency, that rode attached to the main Cassini spacecraft. Its purpose was to descend through the dense, hazy clouds of Titan to see what lay beneath. The probe itself was modest in size, measuring about 1.3 meters wide and weighing 300 kilograms. After it detached from the Cassini orbiter, it coasted through space for 22 days before beginning its entry into Titan's atmosphere. During this silent journey, the only active system on board was a timer, set to awaken the probe just 15 minutes before its atmospheric entry. When it did awaken, the view it revealed was extraordinary. The descent lasted 2.5 hours, and its primary scientific purpose was to collect readings on atmospheric pressure, chemical composition, and wind speed. Because the mission was focused on this atmospheric profile, the lander's batteries were not expected to last long after it reached the surface. Mission planners had considered the possibility of a landing in an ocean or lake and had designed Huygens to accommodate such a scenario. As it turned out, the probe touched down on what appeared to be the bed of a dried-up lake. While Huygens performed its specialized task, the Cassini orbiter continued its own remarkably successful mission for years, returning a treasure trove of scientific data. It also gave us an unparalleled visual record of its journey. Some of the most stunning photographs of space have come from Cassini's cameras, capturing the sublime beauty of Saturn and its moons. The mission's imagery has had such a profound impact that a group of dedicated enthusiasts compiled 1 million of Cassini's individual photos to create a video showing what it would have been like to be a passenger on the spacecraft. These are real images, simply color-corrected and sequenced to show motion, with no CGI involved. As Cassini's fuel reserves began to dwindle, mission scientists started planning how to extract the most valuable data possible from its remaining time. To do this, they commanded the probe to execute a series of daringly close flybys of the planet and some of its moons, bringing it nearer to Saturn and its rings than ever before. This phase began on November 30th, 2016, as Cassini repeatedly soared high above Saturn's North Pole before plunging down to a point just outside the main ring's edge, near the narrow F-ring. It completed 20 of these orbits. Then, on April 22nd, 2017, the spacecraft leaped over the rings one last time to commence its final set of dives, this time through the unexplored gap between the planet and the ring's inner edge. This was the Cassini Grand Finale, a sequence of loops that brought the probe ever closer to its subject, facing increasing danger with each pass, until its data was at its purest just before Cassini flew into Saturn itself. As Cassini prepared for its final embrace with Saturn, its certain annihilation was reframed as an unparalleled opportunity for discovery. NASA officials explained that this concluding phase, the grand finale, would allow the spacecraft to gather extraordinarily rich data, the kind its original planners could only have dreamed of. During its terminal descent past the gas giant, Cassini was tasked with creating detailed maps of Saturn's gravitational and magnetic fields. This information would offer profound insights into the planet's internal structure and could potentially resolve the enduring mystery of how fast its interior rotates. The mission would also dramatically improve estimates of the total mass of the rings, a crucial step toward understanding their ultimate origins. Furthermore, Cassini's particle detectors were set to sample icy ring material as it was channeled by the planet's magnetic field into the upper atmosphere, while its cameras captured breathtaking, ultra-close images of Saturn's clouds and rings. No prior mission had ever ventured into this singular region, so near to the planet itself. The knowledge gained from these final activities was expected to fundamentally advance our comprehension of how giant planets and their planetary systems form and evolve throughout the cosmos. As it completed its last orbit and began its fall, Cassini would fulfill the ultimate objective of its 20-year journey. By destroying itself in Saturn's atmosphere, it would guarantee that the biologically compelling moons of Enceladus and Titan remained forever uncontaminated by any resilient earthly microbes that might have survived the voyage. It was an end that felt at once inspiring, adventurous, and deeply poignant, a fitting conclusion to a remarkable story of exploration. A closer look at these final moments reveals a calculated scientific wager. During the grand finale, NASA willingly exchanged Cassini's remaining lifespan for the chance to achieve unprecedented proximity to Saturn. This was a straightforward decision, as the spacecraft was already nearing the end of its fuel supply, making its long-term survival impossible. With this go-ahead, Cassini was cleared to thread the needle between the planet and its innermost rings, a region never before explored. The perspective it gained was truly unique, offering views that were entirely new. Among the spectacular sights were Saturn's shepherd moons, imaged in astonishing detail. A close pass of Atlas, a 40-kilometer-wide moon orbiting near the outer edge of the A-ring, revealed a truly bizarre world. What is so remarkable about Atlas is its strangely smooth surface, which is almost entirely devoid of impact craters. This curious smoothness is the result of dust from the rings accumulating on its surface, especially around its equator, giving the moon its distinct disc-like or flying saucer shape. A similar process is at work on Pan, Saturn's second innermost moon. At 30 kilometers wide, Pan orbits within the Encke gap, and any ring particles that drift into this 350-kilometer wide path are swept up by the moon. This constant collection of material is what keeps the Encke gap clear and well-defined over time. Another shepherd moon, Daphnis, was not seen in quite as much detail, but its influence is visible for hundreds of kilometers. Only 8 kilometers in diameter, it resides in an extremely narrow channel in the A-ring known as the Keeler Gap. While its gravity is faint, it is just potent enough to stir the nearby dust particles as it passes, generating beautiful waves and ripple effects in the adjacent ring material. At times, it can even be seen pulling a delicate trail of material directly from the ring's edge. These ripples are not just side-to-side motions. They also move up and down, a three-dimensional effect made visible by the long shadows they cast across the rings. It is a scene that sparks the imagination, picturing what it would be like to stand on Daphnis and watch these immense waves follow in its orbital wake with the glorious backdrop of Saturn and its many other moons. The rings themselves were a source of spectacular imagery during the grand finale. One of the most captivating photographs showcases the Janus 2-to-1 spiral density wave. Incredibly, this intricate pattern is the result of the same fundamental process that sculpts entire spiral galaxies, just on a much more tightly wound scale. What appears to be countless individual ringlets is actually an illusion created by just two primary spiral arms, looping around the planet numerous times. Consequently, every other line in the image belongs to the very same spiral arm. This feature is located in the B ring, at a location where ring particles orbit Saturn exactly twice for every single orbit of the moon Janus, creating what is known as an orbital resonance. The photograph also presents a curious illusion, seeming to tilt away at the upper left. But this is not the case. The effect is produced by the way these density waves propagate away from the planet, with their wavelength decreasing as distance from the resonance point increases. The story of this resonance becomes even more mind-blowing. Janus, the moon responsible for the wave, actually swaps orbits with its neighbor, Epimetheus, every 4 years. Each time this orbital exchange occurs, the rings respond by forming a new crest in the wave pattern. NASA scientists explain that the distance between any two crests corresponds to 4 years of the wave propagating outward from the resonance. This means the structure seen here encodes many decades of the orbital history of Janus and Epimetheus. According to this interpretation, the portion of the wave, At the very top left of the image corresponds to the positions of Janus and Epimetheus around the time of the Voyager flybys in 1980 and 1981, the very missions that first proved the two moons were distinct objects. This natural encoding is reminiscent of how a tree trunk records its age through its annual growth rings. It is simply amazing. Beyond these beautiful, detailed images, Cassini also spotted other intriguing phenomena, like the small propeller features scattered throughout the rings. In one image, scientists compared the illuminated top side of the rings with the unlit bottom side to better understand these structures. Even though the image scale is about 500 meters per pixel, the moonlet causing the disturbance might be too small to be resolved directly, though a faint trace of it may be visible in the illuminated view. What is clear, however, is that the moonlet is physically connected to the rings by a band of material. This was not the only such feature. Another was found right beside the Anchor Gap, and a third, likely the largest of the group, was also observed. None of these hidden moonlets are believed to be larger than 2 kilometers across and likely have a density similar to that of a snowball. The last notable discovery within the rings involved extremely small but solid objects that have formed around the E-ring. Their formation is potentially linked to gravitational perturbations from some of the nearby shepherd moons. The rings possess a surprising solidity, having survived numerous impacts that eject fine dust and particles. This material often follows the same orbit, creating a visible haze that can obscure the objects within. As Cassini approached, Saturn's northern hemisphere was at the peak of its summer, offering an unobstructed view of the extraordinary hexagonal feature at its pole. At the heart of this hexagon lies a permanent polar vortex, a storm with the distinct eye wall of a massive hurricane. Intriguingly, the pole appears to have changed its hue with the seasons. A comparison to its much darker appearance in 2012 shows a clear difference. By observing in other wavelengths of light, scientists could also identify additional storms scattered across the planet, along with atmospheric bands similar to Jupiter's, though less pronounced in natural color. The probe's proximity also afforded a unique perspective on the planet's horizon. An image shows a haze in the stratosphere on the left, which gradually fades toward the right. It was believed Cassini would not survive long enough to reach this hazy layer during its final entry. This, however, was not the primary concern for the science team. Their main interest was in discovering the composition of the atmosphere itself. To gather this information, Cassini was destined to plunge into it, burning up and transmitting its final measurements in the process. About a week before this final descent, the spacecraft was still capturing images. The resulting views are nothing short of fantastic. It is worth noting, however, that Cassini could not record real-time video. The moving sequences are time-lapses, crafted from countless individual photographs to simulate what it might have felt like to fly alongside Cassini on its ultimate voyage into Saturn. Not every image from this period was of the gas giant itself. The first time-lapse will examine dates to September 8, 2017, just 7 days before the mission's conclusion. A major focus of Cassini's entire tenure was the moon Enceladus, one of the solar system's leading candidates for harboring life in a subsurface ocean. The probe discovered more than 100 plumes of water erupting from this ocean through the moon's icy crust. This water instantly freezes in the vacuum of space and, over time, has formed the beautiful E-ring that encircles Saturn. This particular ring is incredibly faint and can only be seen when illuminated from behind by the sunday. It may also be the most naturally blue object known in our solar system. Here, we can get a clear view of the influence Enceladus has on the densest section of the E-ring, as its plumes can be seen both disturbing and replenishing the ring's material. Cassini's last look at the plumes of Enceladus was captured in a remarkable time-lapse compiled over a 14-hour period on September 11th. At this point, the spacecraft was near the most distant part of its final orbit, allowing it to assemble a beautiful mosaic in natural light. The thickest of Saturn's rings, D, C, B, A, and F, are all visible, with the planet casting a short shadow across them. Because it was summer in Saturn's northern hemisphere, the planet's most famous feature, the hexagon storm, is presented in its full glory. The subtle atmospheric bands of Saturn can also be faintly discerned in this natural light view. An interesting detail, however, is the dimly lit night side of the planet. This glow is sunlight reflecting off the vast ring system, meaning nights on Saturn's sun-facing hemisphere never become entirely black. Below the glow of the rings, however, the planet is plunged into pitch darkness. As Cassini began its journey back towards Saturn on September 12th, it took images of the atmosphere near the planet's terminator, the line separating day from night. Because the sun is so low on the horizon in this region, enormous cloud structures become visible, casting shadows that stretch for many kilometers. One might think this is a close-up view of Saturn, but the scene actually spans a vast distance of about 5,500 kilometers. Saturn's moon Titan could comfortably fit within this single frame. The spacecraft was drawing ever closer. On September 13th, it took one last look at Daphnis, and observers might notice ripples in the rings both ahead of and behind the small moon. This effect is due to the different orbital speeds of the ring particles and the moon itself. The inner ring orbits faster than Daphnis, so the gravitational disturbances it creates overtake the moon. In contrast, the outer ring travels more slowly, causing the ripples to lag behind. By the time this ring material completes another orbit and approaches Daphnis again, the waves have already smoothed out. On that same day, Cassini took a final survey of the Saturnian system. It captured a view of Titan, a world it had studied extensively throughout its mission. A remarkable place with a dense nitrogen atmosphere. It also looked back at Saturn's rings, with the irregular F ring just visible at the bottom of the frame. As Saturn grew larger in its view, the probe took one last, 40-minute observation of Enceladus before the small moon slipped behind the limb of the giant planet. Cassini's final photograph was of the region where it was destined to plunge into the atmosphere. It was nighttime in this location, and so the clouds below were illuminated by the soft light reflected from the rings. On the final day, photography was no longer on the science team's agenda. As beautiful as the images are, they consume a great deal of valuable bandwidth. The scientists wanted to receive every last bit of real-time data before the spacecraft was lost. This was a unique opportunity, as Saturn's atmosphere had never been directly probed before. When Cassini first made contact with the tenuous outer layers of Saturn's atmosphere, it was traveling at 123,000 kilometers per hour. The remnants of its fuel were used by its thrusters to keep the high-gain antenna locked onto Earth. At this stage, Cassini was 1,900 kilometers above Saturn's clouds. A minute later, those same thrusters were firing at their maximum capacity, fighting to keep the probe from spinning out of control. Cassini was directly sampling Saturn's atmosphere, but that same atmosphere was also causing it to heat up rapidly. Just 10 seconds later, the thrusters were overwhelmed. Cassini began to tumble, cutting off the stream of communication with Earth. At this point, the probe's onboard computers would have tried to diagnose the problem. Gyroscopes and star trackers would have reported the spin, likely triggering a safe mode protocol to divert power in an attempt to right itself. A minute or so after that, the spacecraft would have disintegrated completely, burning up in Saturn's atmosphere. When the final stream of data finished arriving on Earth 1.5 hours later, this last phase of the mission was considered a great success. The Cassini spacecraft's success is measured not just in its active mission, but in the wealth of information it left behind. Its instruments performed direct analysis of Saturn's atmosphere, its ionosphere, and the dust particles within, while also taking detailed magnetic field measurements. An intriguing aspect of the mission is that its data trove may still hold undiscovered secrets. The Cassini project continues to yield new insights, with scientific papers and fresh discoveries emerging as researchers analyze and re-examine its vast collection of observations. But what exactly has Cassini's data revealed in the years following its landmark mission? The findings have, in many ways, only deepened the planet's mystique. You might feel a certain familiarity with Saturn. Its magnificent rings are the most extensive in our solar system, and its hazy, yellow-hued surface is both mysterious and immediately recognizable. We know it as the second largest planet, the one with the lowest density, and the sixth world out from the Sunday. Yet, for all we know, Saturn remains an enigma. A profound mystery resides beneath its obscuring cloud tops, a puzzle brought to light by the Cassini probe that the scientific community has yet to solve. Saturn demonstrates behaviors that our standard models of planetary science suggest should not be possible. From its internal temperature and its magnetosphere to the fundamental length of its day, the question that lingers is what is truly happening at Saturn, and what are our best explanations for these bewildering phenomena? The Cassini probe reached the gas giant on the 1st of July 2004. While it wasn't the first spacecraft to visit Saturn, 3 others had previously conducted flybys. Its mission was by far the most comprehensive. As noted, the orbiter spent 13 years in the Saturnian system, meticulously gathering immense quantities of data with its suite of spectrometers, magnetometers, and other advanced instruments. The knowledge gained has been a monumental benefit to science, but in some cases, it has only served to amplify the planet's strangeness. A striking example is the hexagonal storm at Saturn's North Pole. This vast weather system, spanning 29,000 kilometers, is so large that the Earth could fit comfortably inside each of its 6 sides. What is particularly unusual is that, as far as we can determine, the storm remains fixed at its longitude, traveling with the planet's rotation rather than drifting. This stands in stark contrast to the rest of Saturn's swirling clouds, which are propelled by winds reaching speeds of up to 1,800 kilometers per hour. The storm is an undeniable curiosity, and scientists have yet to develop a complete explanation for its existence. Although some laboratory experiments have managed to create similar hexagonal shapes on much smaller scales. This, however, is not the only puzzle. As the mountains of Cassini's data have been analyzed in the years since its mission concluded, more mysteries have surfaced. It began with what seemed like a straightforward question: how long is a Saturnian day? Despite observing Saturn in our skies for millennia, scientists lacked a conclusive answer. The process isn't as simple as watching a rocky planet turn to see how long it takes for a surface feature to reappear. Saturn's dense cloud cover conceals any potential landmarks on a solid surface below, and these clouds are driven by powerful winds, causing them to move at different speeds than the core. The rings offer no solution either, as they orbit Saturn at varying rates, much like moons, so their orbital period doesn't reveal the planet's rotational speed. Scientists, however, have a clever technique for determining the rotation of a gas giant by examining its magnetic field, and the hope was to apply this method to Saturn. Planets with magnetic fields typically generate them through a dynamo effect. As the planet spins, liquid metal within its core also spins and churns. This immense motion of material creates powerful electrical currents, which in turn generate a magnetic field. A key feature of this process is that the magnetic field's pole is always slightly tilted away from the planet's true axis of rotation. If the two were perfectly aligned, the magnetic field would not be sustainable. Therefore, the standard procedure is to detect the magnetic fields, which Cassini was equipped to do, and then observe the magnetic pole as it traces a circle around the planet's rotational axis. One full circle of the magnetic pole equals 1 day. But Saturn, it appears, does not follow these established rules. Its magnetic pole is aligned almost perfectly with its axis of rotation, with a deviation of less than 0.1 degrees. In defiance of dynamo theory, which suggests this should be impossible, Saturn's magnetic field is robust and active. Its magnetic moment is 580 times more powerful than Earth's and exerts a significant influence over the entire Saturnian system. Scientists are unsure how this magnetic field is generated, as it seems to violate the principles of dynamo theory, and no other proven mechanism can account for such a field. One possibility is that a planetary dynamo is indeed at work in Saturn's core, but some other atmospheric effect is bending the magnetic field lines into perfect alignment with the rotational axis. The alternative is that we are witnessing an entirely new way for a planet to produce a magnetic field. This anomaly sent researchers back to the drawing board in their quest to determine the length of a day on Saturn. Fortunately, radiation measurements offered a more promising avenue. The Saturn system is electrically dynamic, with charged ions flowing between its atmospheric layers and even between its rings and its ionosphere. Scientists observed that Saturn emits radio waves as a consequence of all its interacting magnetic fields, and the intensity of these radio emissions would rise and fall in a regular pattern. This fluctuation seemed to mirror what one would expect to see from a rotating planet. Higher levels of radiation were detected approximately every 11 hours. Based on this, scientists concluded with a degree of confidence that this cycle represented Saturn's day length. An initial estimate, based on data from the Voyager probes, was 10 hours, 39 minutes, and 23 seconds. The expectation was that Cassini could refine this number with greater accuracy. At first, Cassini seemed to be doing just that, but then the data became truly strange. Over the 13 years that Cassini studied Saturn, this measured day length began to change. It drifted by about 1% over the course of a year, sometimes increasing and sometimes decreasing. This observation almost suggested that the planet itself was altering its rotational speed, periodically accelerating and then decelerating. To be clear, a planet as massive as Saturn should not be capable of such behavior. Consequently, scientists concluded that this was not what was happening. Instead, some other effect was once again obscuring the truth about Saturn. An unknown aspect of the atmosphere was causing shifts in the fields, making the radiation fluctuate over time and hiding the planet's true rotation beneath a kind of shimmering veil. A key consequence of the planet's powerful magnetic field is the appearance of auroras that glow above Saturn's poles. However, while on Earth these light shows are a result of the solar wind interacting with our atmosphere, the situation at Saturn presents yet another layer of complexity. Data from the Cassini spacecraft suggested that Saturn's auroras are not entirely driven by the solar wind, as some of these light shows occurred regardless of solar activity. This intriguing detail pointed toward an internal, non-solar origin, hinting at unusual processes at work deep within the planet. Another puzzle was Saturn's own internal temperature, which was unexpectedly high. The planet radiates into space approximately twice the energy it absorbs from the Sun, and while gravitational compression could explain some of this excess heat, another mechanism was clearly required. A compelling, unifying explanation for these interconnected mysteries appears to originate deep inside Saturn's gaseous atmosphere, a revelation made possible by the wealth of information gathered by Cassini. As a gas giant, Saturn is composed almost entirely of hydrogen and helium, but not all of it remains in a gaseous state. Due to the planet's immense mass, the crushing pressure and intense heat increase dramatically with depth, transforming these elements. It is believed that these extreme conditions force gaseous hydrogen into a liquid metallic form, and some scientific theories even propose that this material, or perhaps hydrogen compressed into a diamond-like state, precipitates downward through the interior. The friction generated by this perpetual rain could explain a portion of Saturn's unusual warmth. The remainder of the heat could be linked directly to the auroras, which are thought to be generated by charged particles flowing in from Saturn's moons and rings. Whatever their precise origin, these auroral displays might be powerful enough to significantly warm the planet's upper atmospheric layers. Such high temperatures would inevitably create powerful winds where warm and cold air masses converge. It is hypothesized that these winds transport charged ions throughout the upper atmosphere, and this flow of electrically charged particles could be what distorts measurements of Saturn's radiation, causing the observed fluctuations. This same movement of electrical currents might also solve the puzzle of Saturn's misaligned magnetic fields. One possibility is that a conductive layer within the cloud decks moves at a different velocity than its surroundings, thereby generating its own distinct magnetic influence. It is important to note that these explanations remain theories, lacking definitive proof. Scientists continue to sift through the vast archive of Cassini data for more clues, but a future mission to Saturn may ultimately be required to resolve these profound questions. Fortunately, the long-standing mystery of Saturn's day length has been solved, and the answer was hidden within its rings all along. Researchers shifted their focus from magnetic effects to the planet's subtle gravitational influence on the ring system. The key insight was that Saturn, not being a perfect sphere, exerts a non-uniform gravitational pull. These slight variations in its gravity field create corresponding ripples in the rings, which act as an exquisitely sensitive canvas for detecting these forces. By locating these ripples and carefully measuring the distances between them, scientists were at last able to calculate the planet's precise rotational period. The result is 10 hours, 33 minutes, and 38 seconds, a figure that is now held with a high degree of confidence. While one major puzzle was resolved, many others about Saturn endure. The next mission to the system, NASA's Dragonfly, is scheduled to launch in 2027, but its primary objective will be the exploration of Titan, Saturn's largest moon. Titan holds special interest as it is considered the most Earth-like body in our solar system, featuring a dense nitrogen atmosphere, weather cycles, and lakes of liquid on its surface, though this liquid is methane, not water, and the air lacks oxygen. This focus on Titan means that Saturn's own secrets may have to wait a while longer to be unveiled. For now, the planet's great winds continue to flow across its atmosphere, while a delicate interplay of gravity and magnetism keeps its rings in their perfect, graceful alignment. What stands out is the age of the rings themselves, which are thought to be remarkably young. While the planet is over 4 billion years old, evidence suggests its iconic rings formed only within the last 100 million years. They are also slowly raining down onto the planet, destined to vanish in another 100 million years. This transient nature offers a sense of profound fortune. Had humanity emerged at a different time, we might have missed this spectacle entirely. Witnessing the beauty and unraveling the scientific mysteries of this enigmatic world was a privilege made possible only by the incredible Cassini mission, one of the most significant voyages of exploration in our era. We turn now to Jupiter, a world of colossal storms, intense radiation, and breathtaking beauty. This powerhouse of a planet is so massive that its gravity subtly influences the motion of the Sun itself. It has become one of the most studied destinations in our solar system, visited by 7 flybys and 2 orbiters, with more missions planned for the future. Many fundamental questions remain about this 5th planet from the Sun. Scientists are still working to understand the source of its distinct coloration, its fundamental composition, the nature of the Great Red Spot, and what lies hidden beneath its dense, obscuring clouds. Jupiter also plays a critical role as a guardian of the inner solar system, and its mysteries beckon us to look closer. Located just beyond the asteroid belt, Jupiter occupies the space between the orbits of Mars and Saturn. It circles the Sun at an average distance of 778 million kilometers, or 5.2 astronomical units, taking 12 Earth years to complete a single revolution. The planet's axial tilt is a mere 3 degrees, which means that unlike Earth or Mars, it experiences very little seasonal variation. Similar to Saturn, Its rapid rotation causes it to bulge at the equator, making its equatorial radius larger than its polar radius. Jupiter stands as the largest and most massive planet in our solar system. Its mass measures 1,000th that of the Sun, a truly staggering figure when one considers that the Sun itself accounts for 86% of all matter in the solar system. Jupiter's sheer scale is almost beyond comprehension. Its mass is a remarkable 2.5 times greater than that of all the other planets in our solar system put together. This extraordinary mass gives rise to a fascinating gravitational dynamic. The shared center of mass between Jupiter and the Sun, known as the barycenter, is not located within the Sun itself. Instead, this point lies just above the Sun's surface, at a distance of 1.68 solar radii from the star's center. To understand the concept of a barycenter, it helps to reconsider how we typically imagine orbits. We often think of a smaller body revolving around a much larger one, with the larger object remaining stationary. While this is a useful simplification for something like the International Space Station orbiting Earth, or even Mercury orbiting the Sun, the reality is that the smaller object always exerts its own gravitational pull. The barycenter is the true point in space around which both objects orbit. In most cases, this point is so close to the center of the larger object that the effect is practically unnoticeable. However, given Jupiter's immense mass and its distance from the Sun, its influence is far from negligible. As Jupiter journeys on its long path, both it and the Sun are engaged in a subtle orbital dance around this common center of mass that exists in the space just beyond the Sun's visible surface. A simple analogy can help illustrate this principle. If you were to take a heavy object and a lighter one and connect them with a long, rigid stick, you would have to find a specific balance point to lift them. You would notice that this center of mass is situated much closer to the heavier of the two objects. If you imagine the heavy object is the Sun and the lighter one is Jupiter, with the stick representing the force of gravity, you can begin to grasp how a barycenter functions. While Jupiter holds the title for the most massive planet in our solar system, it is important to note that it is not the densest. Its incredible mass is a direct consequence of its enormous size. To put this in perspective, if the planet Neptune were expanded to the same dimensions as Jupiter, it would actually be more massive. Conversely, if Jupiter were shrunk to the size of our own planet, Earth would be more than 4 times as massive. As it stands, Jupiter's diameter is 11 times that of Earth, and its total mass is 318 times greater. As we know, mass is directly linked to gravitational force, which means Jupiter possesses a colossal gravitational field, more than twice as strong as Earth's at 25.28 Gs at its cloud tops. This gravity is so powerful that its influence is felt by every other planet in the solar system to some extent. Its pull is strong enough to tear apart asteroids that venture too close and has allowed it to capture a vast collection of at least 67 moons. Some researchers theorize that in the distant past, Jupiter's gravity may have destroyed numerous celestial bodies, while also preventing the formation of other potential planets, with the asteroid Vesta being a possible example of this arrested development. Scientists even project that Jupiter's gravitational tug is so significant that it is slowly perturbing Mercury's already eccentric orbit. The models suggest that over a few billion years, this could cause the small planet to either collide with the Sun or be flung out of the solar system entirely. For now, however, Jupiter may be serving as a protector for the 4 inner planets. Without Jupiter acting as a kind of celestial guardian, its immense gravity would not be drawing in or deflecting potentially hazardous objects like long-period comets. It can also perturb their orbits just enough to give them an energetic nudge, sending them on a new trajectory out of the solar system for good. Jupiter is the 5th planet from the Sun, orbiting at a distance 5 times greater than that of Earth. Despite this vast separation, it can appear as the 3rd brightest object in our night sky, outshone only by the Moon and Venus. It is remarkable just how luminous it can be. Even with a simple handheld camera, Jupiter is easily visible as a brilliant point of light. At its maximum magnitude of -2.94, it is bright enough to cast faint shadows on Earth. Because it is so readily apparent in the sky, it has long been a favorite target for amateur astronomers. As consumer-grade telescopes have advanced in recent years, it has become possible to see an astonishing amount of detail right from a backyard garden. What we see as Jupiter's famous patterns are its cloud tops. This atmospheric layer is only about 50 kilometers thick and is composed of ammonia crystals, similar to the atmosphere of Saturn. The vibrant coloration, however, originates from chemical compounds known as chromophores, which are heated deep within Jupiter's interior and rise to the surface. When these compounds reach the upper cloud layers, they react with ultraviolet light from the sun, producing the spectacular, multicolored bands that encircle the planet. This process is part of a continuous cycle, and the appearance of Jupiter's face can change quite dramatically over time. Even as their colors shift, the latitudinal positions of these bands remain consistent enough that they have been given specific names and designations, though their widths can vary over the years. A great deal of turbulence and powerful storms are generated at the boundaries where these bands meet, and this is the very engine that drives Jupiter's most famous feature, the Great Red Spot. This enormous storm is so vast that the entire diameter of planet Earth could easily fit within it. It has been a persistent feature for as long as we have been able to observe it. With the first documented sightings dating back to the 17th century, it is entirely possible that it is a permanent fixture of the planet. An interesting detail, however, is that the storm has been gradually decreasing in size ever since systematic observations began. The exact reason for its distinct reddish color remains unknown, and the hue itself can change significantly, ranging from a deep brick red to an almost completely white shade. The most current theory suggests its color is the result of chemical compounds being broken down by the sun's ultraviolet radiation, a process much like the one that colors the rest of the planet's bands. The key difference is that the storm itself extends much higher into the atmosphere than the surrounding clouds. As a result, its chemical makeup is exposed to far more intense sunlight, which would explain why its coloration can be so much more vivid than anything else around it. Jupiter is home to more than just one scientifically compelling storm, though. Another vortex, known as Red Spot Jr., was formed between the years 1998 and 2000, when three smaller, white-colored storms merged into a single, larger one. So far, it has survived several close encounters with its much larger neighbor, and has become a prominent feature in its own right. It is possible this storm could last for another several hundred years, provided it avoids the fate of a similar storm that was observed passing directly through the heart of the Great Red Spot and was subsequently torn apart. So, what do we believe Jupiter is made of? Much like Saturn, beneath its visible atmosphere lie layers of hydrogen that transition from gas to liquid, and then, deeper still, into a metallic form. As one descends further into the planet, the pressure becomes increasingly immense. Under these extreme conditions, hydrogen begins to behave like a metal. Far below this metallic hydrogen layer, scientists believe there is a core composed of ice or rock. Because we are unable to recreate on Earth the incredible pressures that exist inside Jupiter, we do not yet fully understand what properties these materials would have at the planet's core. It is estimated that Jupiter's composition is roughly 90% hydrogen and 10% helium, with trace amounts of other substances like methane and ammonia. Jupiter also rotates with incredible speed, faster than any other planet, completing one full turn in just under 10 hours. However, because it is not a solid body, it experiences differential rotation, meaning it does not spin at the same rate all over. A full rotation at its poles takes about 5 minutes longer than a rotation at its equator. One might naturally wonder why a planet as massive as Jupiter, composed predominantly of flammable hydrogen, is not a star. It seems logical to think that all it would need is a spark to ignite. The unfortunate news for that line of thinking is that stars do not function quite like a simple fire. Furthermore, there is barely any oxygen to sustain such a reaction. The conditions on Jupiter are not suitable for ordinary combustion, as stars generate their heat through nuclear fusion, a process driven by the immense pressures found in their cores. Current understanding suggests that for Jupiter to ignite as a star, it would need to be approximately 75 times more massive than its present state. Intriguingly, its overall physical volume is not dramatically different from that of the smallest known red dwarf stars. Jupiter also possesses its own ring system, though it is far less conspicuous than Saturn's. There are 4 distinct planetary rings in total. The main ring is notably thin yet bright, while the others are quite broad but extremely faint. This main ring spans about 6,000 kilometers in width, and its most prominent feature is an interruption known as the Metis notch. Another of Jupiter's defining characteristics is its incredibly powerful and expansive magnetosphere, which is 14 times stronger than Earth's. This immense magnetic field, generated by the planet's core of liquid metallic hydrogen, is the strongest of any planet in our solar system, exceeded only by the Sun's sunspots. This has a couple of fascinating implications. First, the magnetosphere funnels the solar wind toward the planet's poles, creating spectacular auroral displays. Second, the 4 largest moons orbit safely within this magnetic bubble, protected from the solar wind. This suggests they do not require their own strong magnetospheres, as Jupiter provides that protection for them. This protection, however, does not extend to all forms of danger. Jupiter is encircled by a truly formidable radiation band, one that has severely damaged probes that have passed through it. The innermost large moon, Io, travels directly through the most intense part of this band, absorbing 3,600 rm of radiation on its surface each day. For perspective, exposure to such a dose would be fatal to a person within 4 hours. Jupiter is known to have 67 natural satellites. Of these, 51 are less than 10 kilometers in diameter. The largest of them, the Galilean moons, are among the most massive in the solar system. These 4 are Io, Europa, Ganymede, and Callisto, each a fascinating world in its own right. Ganymede holds the title of the largest moon in the solar system, with a diameter greater than that of the planet Mercury. An infrared image of Jupiter powerfully illustrates the planet's sheer size and influence. A small dot visible near its southern pole marks the impact site of a celestial object. Had that object struck Earth, it could have triggered a global catastrophe on an immense scale, ending civilization as we know it. This serves as a reminder that Jupiter is not just a beautiful sight, but also a critical component of our solar system's architecture. Transitioning to the outer solar system, we find Uranus, a cold, distant cyan-hued marble that appears barren from a distance. Yet, this ice giant holds a number of fascinating qualities that make it truly unique. One of the first unusual aspects of Uranus is its name. It stands apart from the other planets, which are named for Roman deities. Uranus is named for the Greek god of the sky, Uranos, and the name we use today is a Latinized form of the original. This choice has led to some public awkwardness, as there are 2 common ways to pronounce it, with no definitive agreement on which is correct: Uranus and Uranus. It is also quite special in its orbital and rotational characteristics. As the 7th planet, it orbits the Sun at an average distance of about 19.2 astronomical units, placing it more than 19 times farther from the Sun than Earth is. This distance fluctuates by a significant one: 8 astronomical units over its long year, the largest such variation of any planet. Its remote location means it is exceptionally and consistently cold. with temperatures dropping to -220 degrees Celsius, making it the coldest planet in the solar system. A single year on Uranus lasts for 84 Earth years. When it was first catalogued, astronomers tried to map its orbit. After observing for some time, they found that it did not follow their calculations. They hypothesized that the gravity of another, undiscovered planet was influencing its path. By calculating where this mystery planet should be, they were able to discover Neptune. An intriguingly similar theory is now applied to the hypothetical planet X, or Planet 9. Certain distant objects in our solar system have orbits that don't align with our models, suggesting the gravitational pull of another large planet. The search is currently underway to locate this world. The most scientifically striking feature of Uranus is its rotation. Most planets spin much like a top on the flat plane of the solar system. Uranus, however, appears to have been knocked over and now rolls along its orbital path. Its axle is tilted at an astonishing 97 degrees. This extreme tilt creates seasons unlike any other. During a solstice, when the sun is at its highest or lowest point in the sky, one of the planet's hemispheres is constantly bathed in sunlight, while the other is plunged into total darkness. The planet seems to roll forward in its orbit. At these times, only a very narrow band near the equator experiences a day and night cycle, and even there, the sun barely rises above the horizon. The poles, in contrast, experience 42 years of uninterrupted and constant daylight, followed by 42 years of continuous night. During an equinox, the opposite of a solstice, the planet experiences a more conventional cycle of day and night. Uranus last passed its equinox in 2007 and is now moving toward its next solstice. The planet completes one rotation every 17 hours and 14 minutes. But since its surface is not solid, different parts of its atmosphere rotate at different speeds. Powerful winds can cause some sections to complete a full rotation in just 14 hours. This strange rotation and axial tilt mean that Uranus is the only planet where the poles, on average, receive more solar energy than the equator. Curiously, however, the equator is hotter than the poles, a phenomenon that scientists do not yet fully understand. The reason for the planet's dramatic tilt in the first place also remains a matter of scientific speculation. A prevailing theory suggests that a colossal impact with an Earth-sized planet long ago is responsible for knocking Uranus onto its side, fundamentally defining its character. Among our solar system's giant worlds, it is the least massive, containing the equivalent of 14.5 Earths, which is slightly less than Neptune's 17. Its diameter, however, at 50,724 kilometers, is just a bit larger than Neptune's, and about 4 times greater than our own planets. An intriguing consequence of having its mass spread out over such a vast area is that the gravity at its cloud tops is surprisingly familiar, measuring only 7.8 meters per second squared, or about 0.89 Gs. Beneath its atmosphere, the planet is thought to have a rocky silicate core smaller than Earth, enveloped by a deep mantle of water, ammonia, and methane ices. The term ices is somewhat deceptive, as this layer is in fact a superheated and highly compressed liquid ocean, with temperatures approaching 5,000 degrees Celsius. This composition challenges the simple label of gas giant, since the vast majority of its mass is found in this core and mantle, with the gaseous atmosphere contributing only about half an Earth mass. This atmosphere is composed mostly of hydrogen and helium, but it is the 3% methane that absorbs red light and gives Uranus its signature aquamarine or cyan color. Some scientific models of the planet's deep interior paint an even more remarkable picture. The pressures at the base of the mantle are believed to be so immense that they can break apart methane molecules, compressing the freed carbon atoms into solid diamond. This process could create a continuous, slow rain of diamond hailstones drifting down through the liquid mantle. The very lowest layer of this mantle could even be an exotic ocean of liquid carbon, upon which solid diamond bergs might float. Moving away from the planet, we encounter its subtle and enigmatic ring system. Uranus possesses 13 known rings, all of which are extremely dark and thought to be quite young in cosmic terms, at only 600 million years old. Most are no more than a few kilometers wide and are comprised of tiny particles, the largest being only a few meters across, made of water ice and dark, radiation-processed organic materials. Their albedo, or reflectivity, is less than 2%, which means they are darker than wet soil. It's widely believed the rings are the remnants of past high-speed collisions involving some of the planet's moons. What remains a puzzle, however, is how most of the rings maintain their narrow shape, as the stabilizing presence of shepherd moons has only been confirmed for one of them. The existence of these rings was first discovered in 1977, when astronomers watched Uranus pass in front of a distant star. They noticed the star's light dimmed several times on either side of the planet, confirming the presence of an unseen ring system. Our only mission to visit the planet was Voyager 2" 1986, a flyby that revealed many of the moons and rings of Uranus and gave us our first close-up images of the faint system, bringing the number of known rings to 11 at the time. Years later, the Hubble Space Telescope turned its gaze toward Uranus, discovering 2 additional rings that had never been seen before. The outermost of these new rings is located twice as far from the planet as the previously known outermost ring. As promised, Uranus is accompanied by a large family of 27 known moons, which are traditionally named after figures from English literature. They are divided into 3 main categories: the 13 inner moons, 5 major moons, and 9 irregular moons. The inner moons are intricately connected with the ring system, and some may have been the source for the ring's material. The largest of this group is Puck, at only 162 kilometers in diameter, and it is the only inner moon that Voyager 2 was able to capture in detail. What is remarkable is that these inner moons constantly disturb one another's orbits, creating a very unstable system where future collisions are considered a distinct possibility. The 5 biggest moons, in order of distance from Uranus, are Miranda, Ariel, Umbriel, Titania, and Oberon. Titania is the largest moon of Uranus and the 8th largest in the solar system, measuring almost 1,600 kilometers across. These are generally very dark objects, with Umbriel being the darkest of all. The one exception is Miranda, which is made up mainly of water ice, while the rest are believed to be a mix of water and rocky materials. It is possible these moons have differentiated interiors, meaning a rocky core is surrounded by a mantle of ice. Between that core and mantle, there could very well be an ocean layer of liquid water. An interesting detail is that the axial tilt of these large moons is the same as that of Uranus itself. This means that during a solstice, an observer on one of the moon's poles would see the sun trace a circle in the sky, never setting, which keeps one side of the moon in constant daylight. The final 9 known moons are classified as irregular. They are most likely captured objects on orbits much farther out than Oberon. Their sizes vary from just 20 kilometers to the largest, Sycorax, which is about 200 kilometers in diameter. Finally, we can explore the planet's climate and magnetosphere, which are as unique as its tilt. The planet's extreme orientation gives rise to seasons unlike any other in the solar system. Telescope technology has only been able to resolve details on Uranus for the last few decades, which makes it difficult to say with certainty what changes occur over the course of a full Uranian year. What has been observed, however, is that as the planet approaches a solstice, its pole brightens and a collar of clouds forms, which then dims as the planet moves away from solstice. This brightening is thought to be due to a thickening of methane clouds, although the cause is not fully understood. Seasons also appear to affect storms in the upper atmosphere. Such storms are relatively rare on Uranus compared to other gas giants, but are believed to be triggered by these seasonal changes. With improved technology, we have also been able to observe bands stretching around the planet, much like on other gas giants. However, these bands are mainly visible in infrared light, which is why Voyager's cameras only showed us a featureless blue-green sphere. In these infrared images, you can also see small storms dotting the surface. Another unique feature of Uranus is its unusual magnetosphere. Typically, a planet's magnetic field originates from its geometric center, but this is not the case for Uranus. Furthermore, it is not aligned with the rotational axis but is offset by 59 degrees. This strange placement means the magnetosphere is much stronger at the North Pole than at the South. One theory for this is that a liquid diamond ocean could be deflecting the field, or perhaps the field is not generated by the planet's core at all, but rather within its conductive liquid mantle. Neptune possesses a magnetosphere with a strength comparable to that of our own planet, but its unusual rotation twists its vast magnetic tail into a corkscrew that stretches for millions of kilometers out into space. When we gaze into a clear night sky, most of the planets in our solar system can, at various times, be seen with the unaided eye. The sole exception to this is Neptune, the smallest of the gas giants and the most remote outpost of the Sun's family. This world presents a profound puzzle. A planet so distant from the Sun's life-giving warmth ought to have a placid, inactive atmosphere, yet it is a dynamic place of colossal storms and impossibly fast winds. The question of what fundamental forces drive this distant, turbulent world is one of modern planetary science's most intriguing mysteries. The story of Neptune's discovery is entirely unique in the annals of astronomical history, as it was found not by serendipitous observation, but through the pure power of mathematical prediction. After the planet Uranus was identified, astronomers meticulously tracked its celestial path, only to find that its actual orbit displayed subtle but persistent deviations from their most precise models. In 1846, the brilliant astronomer Urbain Le Verrier deduced that these gravitational perturbations must be caused by the influence of another, as yet unseen planet, and he went on to calculate its likely position in the sky. Remarkably, when Johann Galle aimed his telescope toward that specific region of space, he located Neptune within just 1 degree of Le Verrier's predicted point. Only a few days after this stunning confirmation, Neptune's largest and most famous moon, Triton, was also discovered. For more than a century that followed, our collective understanding of Neptune remained frustratingly limited. Its immense distance from Earth and its consequently tiny apparent size in our sky made any detailed study with ground-based telescopes an exceptionally difficult undertaking. This long period of mystery came to an end in 1989, when the Voyager 2 spacecraft executed its historic flyby, providing a wealth of new and transformative information about the ice giant. For the very first time, humanity could gaze upon the planet's mesmerizing, deep blue face in stunning detail, confirm the existence of its faint and delicate ring system, and identify a whole host of previously unknown moons orbiting the distant world. Since the formal reclassification of Pluto, Neptune officially holds the title of the 8th and most distant planet from the Sun. It follows an enormous, sweeping orbit at an average distance of 30 astronomical units, which is to say it is 30 times farther from the Sun than the Earth is. This immense void translates to a staggering 4.5 billion kilometers, a scale so profoundly vast that a modern space probe, utilizing our current propulsion technology, would require approximately 13 years to complete the arduous journey. Its orbit is so long that it takes a full 165 Earth years for Neptune to complete a single trip around the Sun, which means that we have observed only one full Neptunian year since the moment it was first identified by humanity. This great distance from its star results in an incredibly cold average atmospheric temperature of -201 degrees Celsius. An intriguing detail is that Neptune has an axial tilt measured at 28 degrees, a figure that is remarkably similar to Earth's 23 degrees and the 25-degree tilt of Mars. This similarity means that, like Earth, it experiences distinct and predictable seasons. The key difference, of course, is their immense duration. Each of Neptune's 4 seasons lasts for an astonishing 40 Earth years. At this moment in time, the planet's southern hemisphere is in the midst of a long and gradual spring, a period during which it receives more direct sunlight and, as a result, appears noticeably brighter in our telescopes. What is particularly remarkable is that this brightening effect occurs despite the fact that the Sun is 900 times dimmer at Neptune's orbit than it is at Earth's. Even this faint increase in solar energy has a significant and measurable impact, warming the southern hemisphere by about 10 degrees Celsius compared to the rest of the planet. This slight warming is just enough to cause frozen methane gas to sublimate, allowing it to rise from the lower troposphere into the stratosphere above, which in turn causes the observed increase in the planet's brightness. The weather on Neptune is, by a wide margin, the most extreme found anywhere in the solar system. Winds at the planet's equator have been measured, blowing westward at an astonishing 2,160 kilometers per hour, a velocity that approaches supersonic flow. Curiously, most of these powerful winds travel in a retrograde direction, which is opposite to the planet's own rotation. Alongside these incredible winds, Neptune's atmosphere is marked by distinct cloud bands and truly colossal, swirling storms. When Voyager 2 flew past the planet in 1989, its cameras imaged the Great Dark Spot, a massive storm system that was roughly the size of our own planet. It also observed a smaller storm to the south, which was dubbed the Small Dark Spot, that appeared to change its hue from dark to light as the probe drew nearer. When the Hubble Space Telescope was later aimed at Neptune in 1999, astronomers were eager to learn if these storms were permanent fixtures, akin to Jupiter's Great Red Spot. They discovered instead that both storms had vanished completely, revealing that Neptune's powerful weather systems are surprisingly transient, with giant storms and bright, high-altitude clouds continuously forming and dissipating over time. This observation raises a compelling question. Why is Neptune's atmosphere so turbulent when its sibling planet, Uranus, which is very similar in size and composition, is comparatively calm? While Uranus does have fast winds of its own, reaching up to 900 kilometers per hour, they do not begin to match the extremes routinely seen on Neptune. The subtle interaction with the distant Sun and the planet's long seasons alone cannot fully account for this stark difference. Something else must be at play, driving Neptune's weather from within. The answer may lie deep within the planet's mysterious interior. A key distinction between the two worlds is that Neptune radiates a significant amount of its own internal heat, whereas Uranus, which is actually the coldest planet in our solar system, radiates almost no excess heat at all. One leading theory suggests that billions of years ago, a massive body the size of Earth may have collided with Uranus, stripping it of its primordial heat. Astronomers now believe that Neptune's more active and dynamic weather is fueled, in large part, by this higher internal temperature. In terms of its fundamental makeup, Neptune is thought to be a close cousin to Uranus. Its atmosphere is composed primarily of hydrogen at about 80% and helium at 19%, with trace amounts of methane. It is this small fraction of methane that absorbs red light from the Sun and gives Neptune its characteristic and beautiful deep blue color, a much richer shade than the pale cyan of Uranus. Beneath the atmosphere lies a liquid mantle made of water, ammonia, and methane ices, which surrounds a solid core. At the boundary where the core and mantle meet, the pressure is thought to be so extreme that it may break down methane molecules. This has led to a fascinating theory that deep inside Neptune, diamonds are formed under this immense pressure, perhaps not as familiar as solid gems, but as a liquid carbon ocean where solid diamond bergs might float. It is even possible that diamonds rain down through the mantle like hailstones. While this remains a theory, recent technological advances have begun to recreate the incredible pressures near Neptune's core, estimated at 7 million bar or 700 gigapascals, which is roughly 7 million times the atmospheric pressure we experience on Earth. When observing the solar system's ice giants, a curious parallel emerges in their magnetospheres, particularly in the case of Neptune. The planet's magnetic field is dramatically misaligned, tilted at a remarkable 47 degrees from the axis around which it spins. When the Voyager 2 probe first encountered a similar phenomenon at Uranus, the initial hypothesis linked this oddity to that planet's extreme axial tilt. However, this theory was reconsidered when the spacecraft arrived at Neptune, which has a much more conventional axial tilt, yet presented the very same kind of magnetic offset. This discovery led scientists to develop new ideas. The prevailing theory now suggests that Neptune's magnetic field is not generated deep within its core, as Earth's is. Instead, it may originate in a churning, electrically conductive liquid mantle closer to the surface. An alternative explanation posits that the field is indeed born in the core, but that the overlying mantle actively deflects it, creating the pronounced and unusual angle relative to the planet's rotation. While it's true that no planet in our solar system has a perfectly aligned magnetic field, even Earth's magnetic north wanders from its geographic North Pole. The extreme inclinations seen at Uranus and Neptune place them in a class of their own. This unique magnetic orientation has a direct effect on another of Neptune's atmospheric phenomena, its auroras. The lights that dance in Neptune's sky are profoundly different from those we might imagine. They are exceptionally faint, a result of solar particles arriving with less energy after their long journey from the Sunday. Furthermore, the tilted magnetosphere funnels these particles in unusual ways, shaping the resulting auroral displays. What appears are predominantly type B auroras, or what are known as stable auroral red, or SAR, arcs. Earth experiences these SAR arcs as well, but they are completely invisible to the naked eye, detectable only with specialized scientific instruments. One could be stretching across the entire sky above us without anyone ever knowing. A key distinction with Neptune's SAR arcs is their location. Rather than being confined to the polar regions, they manifest around the planet's mid-latitudes, a direct consequence of its skewed magnetic field. Moving outward from the planet itself, we encounter Neptune's subtle and elusive ring system. Like the other gas giants, Neptune is girdled by rings, but they are incredibly faint and difficult to perceive. They lack density and are composed of extremely dark material, making them nearly invisible against the black backdrop of space, especially at such a great distance from the illuminating light of the Sunday. In total, 5 distinct rings have been identified, each named for individuals instrumental in the planet's discovery and study. The innermost is the Gale ring, a very diffuse and wide structure, measuring 2,000 kilometers across. Beyond it lies the Leverrier ring, which is considered one of the brighter rings, though it is quite narrow at only 113 kilometers wide. Connected to this is the Lassell ring, a faint, broad band that spans 4,000 kilometers. Situated on the outer edge of this band is the Arago ring, which is slightly more luminous than the Lassell ring and measures less than 100 kilometers in width. The final and most distant of the main rings is the Adams ring. At just 35 kilometers wide, it is nonetheless one of the brightest and has been the subject of considerable research. The Adams ring is particularly intriguing because it is slightly inclined and, most remarkably, contains several bright, concentrated arcs. These clumps of material have remained surprisingly stable since their discovery in 1980, a feature that defies expectations, as planetary rings are typically uniform. The mechanism causing this material to cluster together remains one of Neptune's unsolved mysteries. The story of the Neptunian system continues with its moons. There are 14 known satellites orbiting the planet, all named after water deities from Greek mythology. The most famous, and by far the largest, is Triton, a world so massive that it contains the vast majority of the mass of all Neptune's moons combined. Its surface is a captivating canvas of incredible patterns and a distinct burnt orange hue. What makes Triton scientifically compelling is its orbit. It travels in a retrograde direction, opposite to Neptune's rotation, and at a significant inclination. This orbital path is strong evidence that Triton did not form alongside Neptune but was instead a wandering object from the outer solar system that was captured by the planet's gravity long ago. It has been theorized that Triton's violent arrival may have been responsible for creating Neptune's rings, as its gravitational influence would have catastrophically disrupted the orbits of any pre-existing moons, causing them to collide and shatter into the debris we see today. Triton itself is a substantial world, larger than the dwarf planet Pluto, and it possesses its own tenuous atmosphere, where Voyager 2 even observed faint, wispy clouds during its flyby. Beyond Triton, the next largest moon is Proteus, an object notable for its irregular, lumpy shape. Such a non-spherical form is common for small asteroids. But Proteus is quite large, measuring 400 kilometers across, even bigger than Saturn's perfectly spherical moon Mimas. Its rugged appearance is a testament to a violent past, with immense craters from colossal impacts preventing it from settling into a rounder shape. Closer to the planet, a collection of inner, regular moons orbit within the ring system, with some acting as shepherd moons that help to contain the ring particles. Farther out, the irregular moons are all thought to be captured objects, much like Triton, with some orbiting prograde and others retrograde. The most extreme examples of these are Neptune's outermost moons, Psamathe and Neso. They hold the distinction of being the most distant satellites of any known planet. Their journey around Neptune is a slow and immense one, requiring a full 25 years to complete a single orbit. This is possible only because of Neptune's enormous hill sphere, the region of space where its gravitational pull dominates over the Sun's. Because Neptune is so far from the Sun, the star's gravitational influence is significantly weaker there, allowing the planet to hold onto these remote moons in their vast, lonely orbits.